So good morning, everyone, and thank you for coming to our talk. My name is Jordan. It's my coworker, Jorge.
Hi.
And so we're going to talk about releasing a C++ toolchain today. And we're going to talk about it in this context live at Head. So if you haven't already, you should go watch a talk by Titus Winters from CppCon 2 years ago. It's a really good talk. And he talks about having a live at Head code base where the essential idea is instead of depending on some old, quote, stable version of some software library, instead you depend on trunk. You avoid problems like the diamond dependency pattern, things like that. But what we want to talk about is applying this to your toolchain as well. So instead of depending on that old, stable toolchain you like from 2 years ago, depend on trunk. So in this talk, we're going to talk about our own release process, but the goal here is to try to keep it general. We want you to leave here with the idea of how you can apply this to your own release process. So as mentioned before, we're from the C++ Production Toolchain team at Google. We're based in Sunnyvale, but we have lots of friends working on C++ all over the world. Just want to shout out to our C++ tools team in Munich. They're awesome. But what does this mean? So when we talk about a toolchain, we want to make it clear we're not talking about just the compiler. Obviously, that's a very cool thing that we all like to talk about, but that only gives you an object file, right? You need an actual compiled binary, so you need a linker like gold or LD to give you an executable. You need binary utilities like obj-copy, AR, NM, those things, to manipulate and understand your binaries. And you need a C++ standard library so you can actually use things like map and vector and all those things. So when we talk about releasing a toolchain, we're talking about all these things together. And the word production, it's a little odd actually. So we have a bunch of teams at Google that all have their own requirements, like Android, iOS, and Chrome developers. They all care about different platforms and they want to build their binaries in different modes. And so they actually have their own tool chains that we call non-production, which is weird because they're totally production quality. They're great tool chains. But when we talk about production, we're speaking of like the classic well-known Google products like Search, Ads, and Gmail. These are like the bulk of the jobs that run in the data center.
Okay, so when I first joined the team, I was thinking, okay, this is all very serious business, so we must surely be using the most stable, like pinned to a years old version, tried and true of the compilers, right? And the answer is this, like, no. We pull from head and upgrade our toolchain every week or 2 weeks if there are some issues and we are slower. And this was me when I learned that. So I had a lot of questions because at my previous job, I wasn't even using the last version of Visual Studio because people were afraid to upgrade. And questions like, doesn't everything break? Or don't your users get mad? Or how can you make a toolchain built from head really stable? Or why would you do this? Like, is it worth it?
So obviously we're here and we think the answer is yes, right? But let's talk about why. And the key really comes down to shorter feedback cycles, right? If you're depending on a toolchain from 2 years ago, then your feedback cycle is 2 years. We live at Trunk, so our feedback cycle is just days or maybe weeks in the worst case. And so obviously you get the good things sooner, but just as important, it is a complete feedback cycle. And if there's something bad that happens upstream, it's easy to notice it right away and fix it. And you submit that fix upstream and pull from head again. So for example, performance, obviously. C++ is a performance programming language. It's much better to have your job continuously get 1% faster than wait for just a bump at the end of the year. Like, first of all, like, we all love faster services. Your users love faster services. The people paying for your data center or costs are going to love this because it means your power bill goes down. And performance is also a cumulative metric. So if you if you release your toolchain after a year and you're like, oh, great, I got this 10% performance win. This is awesome. What you might not realize is that you could have had a 12% performance win, but there was a 2% regression in there that you missed. And so if you have a shorter feedback cycle, then you're much more likely to catch these 2% regressions, because every release is only going to be plus or minus 1 or 2%. Diagnostics and sanitizers are really, really awesome tools. So, we all know that C++ is a very difficult language, and it's very easy to write the wrong thing. And so diagnostics and sanitizers, they're sort of two different infrastructures, but from a release testing perspective, they kind of fulfill the same purpose. Diagnostics tell you at compile time that your code is probably wrong, and sanitizers tell you at runtime that, for instance, you're iterating over an array, but you accidentally went one past the end. And these save countless bugs at Google. I wouldn't be surprised if somebody told me that ASAN found half our bugs. But of course, these can also be false positives. So again, if you can identify these quickly, it's much easier to fix and revert upstream. And if you attended Devin and Zola's talk on Monday, you would know about Spectre, and you can know about how the compiler can actually help you generate mitigations to handle untrusted user data. So security fixes are an obvious case where you want this sooner rather than later. And of course, the delta for every toolchain update is just much smaller, which means it's much easier and it's less risky to apply these upgrades. But I know you're all thinking, like, what about all the bugs, right? That's why you aren't upgrading, or one of the reasons you aren't upgrading. And I'm not going to sit here and lie to you and tell you that the compiler and the toolchain is bug-free. Like, I can tell you that it has a lot of bugs. But the reason it has bugs is because it's software, right? And this is just an essential fact that all software has bugs, right? Your kernel has bugs, the code you write has bugs, and everything in between has bugs. We don't think it's a really practical stance to say, we're just going to bury our heads in the sand and only take the stable things. You don't really make that much progress. Instead, we think a better approach is to use things like testing, better testing approaches, have good sanitizer coverage, things like that, and just use regular software engineering. And when you live ahead, it means that bugs are easier to find and they're easier to fix. And in fact, we do that a lot. So this is sort of a teaser for the rest of the talk. We have millions of tests that people write, not for the compiler, just their own projects, each with tens or hundreds of test cases. So we have a large testing code base. We have hundreds of millions of lines of C++ code that gets fed to the compiler. So the compiler sees all sorts of weird files. It's a major stress test. And it usually takes a couple days to revert patches. So sometimes I feel like we're like a second layer build bot. So upstream has build bots to run the compiler tests, and then it comes over to us, and we come up with the weird regression test that people didn't think of. Okay.
All right. So before going deeper into details of how our release process works, first we need to give you a few background facts about how Google works with respect to the developer workflow. Most important thing is that everything lives in the same repository. This is a pretty widely known fact. And we built almost everything from source. And this has the interesting consequence for us that we can fix our users' code. So one of our goals when upgrading the toolchain is that our users won't notice. That is, unless we tell them that we have a new cool feature for them to try. So because we can go and fix their code, any of the cases where things can go wrong that we will explain later, we can actually go and fix our users' code and make them transparent upgrades. Also, we have a build and test farm for continuous integration, and we can run all the tests in the code base as a pre-submit. And we have this strict testing culture codified by what we call the Beyoncé rule. Beyoncé has this song saying, if you like it, then you should have put a ring on it, and we say, put a test on it. And that means that we can test everything our users care about. So, because this rule is very strictly enforced, if any upgrade of us or of the people maintaining common infrastructure and libraries breaks anyone. If there is a test, that's the responsibility of the person making the change. If there isn't a test, no one cares. I can break it, and everything's fine. And finally, we use an LLVM-based toolchain, but this is not an LLVM talk. We hope that all of the process we described here can be applied with any other toolchain. If you are not using open source, you won't get the same commit-by-commit granularity that we get for tests, but still you could be able to apply it to your vendor's release schedule and try to work with that. So what is a release? We store the toolchain binaries in the repository, and that has a couple of nice properties for us. The most important of which is that we can go back in history at any point in time, in the history of the repo, sync there, and rebuild a binary, and we will use the exact same toolchain at the time, and we will produce the exact same binary byte by byte. So repeatable builds. And therefore, when we talk about releasing, this means we are submitting a change to the repository with the new updated binaries. And then from that point on, all users will start using the new thing.
Okay, so that's a very quick overview of our infamous monorepo. And so I'm going to give you another quick overview, this time of how a toolchain change lands in our system. So as mentioned, we're an LLVM-based toolchain, so the process starts when a developer submits something upstream, and this is an external repository. The next thing we want to do is we want to ingest this internally. So we have a bot that picks up this commit after just a couple minutes. It doesn't really do much, it just puts it in an internal repository so that our source control tools, which know how to navigate it across revisions and branches, know how to deal with it. And we don't have anything like an external network dependency in our build system. And this goes into a long-lived, pristine development branch, so users don't submit code here. So we don't run unit tests at all specific revisions, but we do build a full toolchain, which I think is really cool. And it makes it really easy to very quickly pull out a toolchain at a specific revision and see what happens. And we'll get to this later. And this toolchain it's a basic release toolchain, which means we just take the stable compiler and build it in opt mode with like 03 or whatever it is. And so it's just a stage 1 build. Next thing we want to do is put it in a place where people can actually use it. So this is where we have 2 rotations on our team. And the first rotation, the build cop, they integrate it into the main line of the monorepo. And at this point, they run the full compiler test suite. And if there's a problem, they'll fix or revert upstream and try the process again. When they do this, because we are a live-at-head repository, we also update all the callers. And this doesn't always happen, and when it does happen, it's usually trivial, like a method rename. But the second thing that the build cop does is they build and they actually update the unstable toolchain. This unstable toolchain is built in the full production release mode. So it's a 2-stage PGO build, which means we first build it with the stable toolchain, and then we build it again with itself. And in fact, we build it one more time to make sure that it was a deterministic build. And it uses PGO, which is profile guided optimization. So we actually build it once, tell it to go compile something, and then we use that profile to make better optimization hits the second time around. And the purpose of this is to make it really easy for developers to quickly try out the beta compiler. Mostly compiler developers wanting to make sure that their fix actually worked. So next thing we want to do is we want to try to promote this from unstable to stable. So the release cop creates a short-lived release branch, and this is opposed to the long-lived pristine development branch. And this branch is created solely for this one release. As soon as the release is done, we'll just throw it away. During their testing, they'll probably find some bug and revert something upstream, and we'll cherry pick it straight from the development branch to the release branch without waiting for it to integrate to mainline. And we'll do this a couple times. If it gets too messy, then we'll just throw away the release branch and try again. Finally, once they've done all their testing, they take the binaries that they've built on the toolchain release branch and just copy it over to mainline. And once this change is submitted, then the release is complete. As Jorge mentioned, all builds after this point in time are using this new toolchain. So I went through that really quickly and left in a few giant question marks, like how do we make sure nothing breaks, right? Very important questions. So I'm going to share you a super confidential screenshot of our release testing script. And credit to Ali Brosh for the all the things character from this old comic. So what do? Build and test all the things. So as Jorge mentioned, we have the Beyonce rule where people said, well, I care about my code, so I'm going to write some tests. And so we take all those tests and we run them. And so this is millions of tests that people said they care about. So we make sure it passes with the new toolchain. And we could be done here, right? We've made sure that what people care about is passing. Normally this is fine. But we actually want to go beyond the Beyonce rule. We want to add some robustness testing to our process and make sure that we aren't just testing the basic default configuration. So we want to test it in all the configurations we care about. So this would be things like sanitizers or targeted for different microarchitectures, different optimizations or debug levels, things like that. And so this lets us, this gives us some confidence that the toolchain works in other ways besides just the default mode. And we want to save our sanity, so we have a lot of automation around this. In fact, every Friday night, without any human intervention, we automatically create a release branch, build the binaries, run all the tests, and we'll talk about this later, but we even automatically have a list of all the tests that failed and upstream revisions that are the possible culprits that we should look at.
Then the other kind of testing we do is performance testing. And I'm gonna make a little diversion here to tell you about some ways I found while working on this at Google, how benchmarks and performance tests are closer to regular tests that I thought at first time. And this could be a whole 1 hour talk in itself, but I'm gonna gloss it over more or less quickly. So as we all know, tests allow us to make changes to the code base while preserving correctness. And benchmarks allow us to do the same thing while preserving performance. Also, we need a mix of unit tests and integration tests. You know, unit tests are smaller, easier to reason about, easier to run, also consume less resources to run. But there are some things that only happen at the level of the whole system when everything's running. So for the same reasons, we need a mix of micro and macro benchmarks. Micro benchmarks are easy to handle. But there are some performance effects that can only be observed with the whole system running. So you need some kind of integration test, but for benchmarks. Also, when writing a test, it's important to test only the things that actually matter. It's really easy to accidentally end up testing some things that you don't care about, like implementation details, for example. We will have some more about this later. And the same happens to benchmarks as well. If you are not careful, it's easy to get the compiler to remove the whole loop you are testing because maybe you don't produce any output from it. And it's also important to measure the things that actually matter to you because sometimes you have some metrics available to you that are easy to measure, like, for example, CPU cycles and whatnot. But it's important to not lose track of the things that actually matter to your project, like, for example, queries per second or latency. Finally, we all know that flaky tests are bad, and the same thing applies to benchmarks. Now, when I say noisy benchmarks here, that doesn't mean that there's not going to be any noise whatsoever. What I mean is that results should be reproducible, because if you have a benchmark that tells you there's a regression and you rerun it and then it tells you, no, there's not a regression anymore, then it's worse than having nothing. You are wasting time. But not everything's the same. And the differences can be summed up as mostly benchmarks are fuzzier. So a benchmark gives you a number. when you have a test, you have a clear pass or fail signal, and you know that when something fails, you have a bug and you have to go and fix it. But if a benchmark tells you your code is now 0.5% slower, is that a bug that you have to go and immediately fix and block the release on it? Maybe. What about a 1% or 10%? And also, you cannot even make this kind of performance decision in isolation. You have to consider all your benchmarks, the performance of all your code base, because maybe something got 1% slower, but overall you have a 2% win. So maybe you want to keep that compiler revision. And finally, if you like it, put a benchmark on it. Same thing. This is usually quite easy because people working on performance like to show pretty numbers to show their work and get promoted. So that usually works well. So now onto the details of what we actually do. We have 3 classes of benchmarks we run and care about. As I mentioned, there's micro benchmarks and macro benchmarks for code that runs inside Google that are representative of our loads. Micro benchmarks are for hard code, either because they consume a lot of CPU or they are in the critical path for latency. And here we have also 2 big classes, things that are a big part of individual projects. Like if you are doing any machine learning, you will do a lot of matrix math and you want it to be fast. But there's also things that are not a big part of anything, but they are a considerable part of the total data center load, like protocol buffers or compression or hash maps. So we also test that. We also have a few macro benchmarks. For example, we bring up a whole search server and do a load test on it. And this is expensive, but it's worth it. And finally, we have some public benchmarks. We try to run every open source benchmark we can get our hands on. And even though they are not representative of the computing loads at Google, they are very useful as a communication tool. Because if we have some internal regression, then we cannot go and tell some upstream developer, hey, here's our code, it got slower with your patch, please help us. But if some public benchmark regresses at the same time, we can use that as a proxy. Now, what's our benchmarking setup? Here we focus on reproducibility, because as I said, if something doesn't reproduce, we cannot debug it or triage it effectively. So we had our first try was something like this. We put some production-like machines in a dedicated cluster, so no one could come and run jobs on them, except us. Then we set up the software, so we did multiple runs of every benchmark, and then get some statistics and get some confidence intervals for our A/B test. Very basic stuff, really. And then at some point, we decided to run an AA test to see how noisy it is. That is an A/B test, but running the same binary on both sides. And we got something like this. Here, this is a compression benchmark. Every point here in that graph is a metric reported by that benchmark. It's all normalized with respect to the baseline. So the center line is the baseline, and then every dot represents a single metric. For example, this is a compression benchmark, so we have compression and decompression for different kinds of data sets. And as you can see here, everything is more or less in between the plus and minus 2% mark. There's one outlier, one weird thing about almost 5%. And this is not good. It's also not terrible, because all the confidence intervals are overlapping, so we are not flagging a regression in an AA test, which would be really bad. But still, it's hard to think that if we had a real regression in here, we would be able to see it unless it was very big. So we started tweaking things. For example, we have, as I said, this was a production-like machine, so it has some fleet management software, and these processes were sometimes interfering with our benchmarks. There are also some operating system settings that you can tweak because they can have some performance on, some impact on performance. For example, address space layout randomization, or ASLR. We also tweaked how our CPUs did frequency scaling, because that can alter your benchmark results in unpredictable ways. Then we tweaked, instead of doing the same number of runs for every benchmark, because not all of them are equally stable. We tweaked individually the number of runs to get somewhat stable results, and also dry runs. So for some reasons, the first time you run a benchmark, it's highly likely that you will get slightly different results. So just running it a couple of times before actually measuring things helps, just discarding the results of that. And finally, a note that helped me: if you cannot stabilize something, it's better to randomize it. So sometimes you see some bias in your results, and maybe you don't know what is causing them, or you cannot go and fix it because it's not easy for you. In those cases, if you randomize the effect, you can spread the noise around, and you will have noise instead of bias, which is a little better. So for example, we had some issues where we did 10 runs of A, 10 runs of B, and they were different. If you interleave them in a random order, then whatever's causing this thing will be spread across the two variants. So after applying all these things, we went from something like this. Again, every point here is an individual metric. We went from something like this to something like this, which I think it's pretty acceptable. It's still somewhat noisy, but we can live with that. And at some point, while doing this kind of tweaks and configuration adjustments, you get to a point where you get diminishing returns. So it's not worth going and fixing every last bit of noise. So if you don't care about regressions higher than 0.5%, because also compiler developers need some wiggle room to improve things, then you can stop here. And that's what we did. And finally, when you have a lot of benchmarks, it pays off to invest in visualization tools and filtering tools and reporting tools. Because, for example, we have tens of benchmark binaries. Every binary reports multiple metrics, like here. We also build them for several platforms, different microarchitectures and such, and several build configurations. We do plane optimized builds, we do profile guided optimization. So we have a combinatorial explosion here, and it can take a significant time to just go over all the results and try to see if there's anything odd. So we have some automatic filtering, we have some custom dashboards, and also these graphs I just showed you were developed by our team.
Yep. So that's sort of the process of how we test things and how we benchmark things. And once that all looks good, then it's time to ship it. But of course, there's always something that comes up. So we have tons of failures and regressions. They might be build breakage, performance regression, test failure, whatever it is. And we think there's three basic things that apply to a lot of these situations. First of all, you want to start out by deflaking things. Right? If you're running millions of tests, running hundreds or thousands of benchmarks, you're going to have random noise in the system. So don't waste time on those. Just rerun it. Make sure it's actually reproducible before you actually invest time in it. The next thing we do is we identify the revision. And so this is where those pre-built development tool chains come in handy, because it lets us really quickly go to specific compiler revisions and test if something is reproducing there. And because it's pre-built, we can do this in a logarithmic fashion, just bisecting to one revision. And the last question, though, is interesting because it's not always the revision's fault, right? A lot of times it's actually an existing issue with the code that the toolchain is actually just getting smarter at telling you about. So let's finally look at some code. So you have this beautiful method here, lots of great variable names. You get some things, you check if it's what you expect, and if it's not what you expect, then you print a warning. So this looks fine. Let's run it, and let's ignore warnings for now, because who needs those? And then you get this, right? Now, I'm sure, if you've been programming C++ for a while, I'm sure you can find the bug, but this is very clearly not what you meant to do, right? And this is something that if somebody gave you a 500-line code review could easily, be missed. So let's let the compiler help us. So this is actually the string plus int warning, which tells us that when you take a string and add it into it, it's not actually string concatenation. In C and C++, this is array indexing because the error message is actually a character array. And the expected value is your offset into that array. So kind of surprising. We obviously didn't mean to do this. So this was actually an improvement to an existing one. So you may see compiler diagnostics get smarter, or you may see new ones come up. And these fix tons of real bugs all the time like this. This is just a bad log message, but it could be real. And just as a side note, one common strategy we see with these is sometimes the compiler breakage is pretty widespread. So you might just want to disable the warning temporarily. And that way you can do a cleanup without blocking the release process. Another thing the compiler does is it crashes. This is not very useful for a compiler to do. Now, I don't know what a predecessor is or why it has to be dead, and I'm sure many of you in the audience do know. But you don't need to tell me. All I care about is that I have my super secret algorithm and I can't build it. And I want to revert this upstream, but I can't give you my super secret algorithm to reproduce this issue. So what do I do? Fortunately, there's a lot of really good open source tools out there. We use CReduce for C++, and you can use LVM reduce or bugpoint for LVM IR code. And the way these tools work is you give it an interestingness test. So we would say, this test case is interesting if you compile it and it fails with this specific compiler warning, or this compiler error message. And this looks really, really weird. Like, it doesn't make sense. It's undefined behavior, but I don't really care again because it reproduces my issue. So now I actually have something to give upstream. And you can't figure out what my confidential algorithm is, except that we use for loops. So, oops. And just a side note, if you're attending the LVM developer conference and you want to hear about LVM reduce, it's a very new tool in the LVM community. Diego Trevino, the author of it, will be giving a talk on it. And of course, there's a lot of other sad things the compiler can do. It can make all your files bigger. It can use all the resources on your machine. You might load your unit test and debugger and find all the variables are gone. So lots of bad things it can do. And if they're severe enough, we'll block the release on it. And these actually fit into the same bucket as compiler crashes because we just have to craft a different interestingness test. So if you're debugging a compiler timeout, you just set your interestingness test to say, if it went from 2 seconds to 5 minutes, then just say, this test case is interesting if it takes more than 15 seconds to compile. And some more fun code. So you can get a C++ language lawyer to give you a good definition of undefined behavior. But the definition I really like is undefined behavior is code that accidentally worked. And this is a very fresh example we ran into 3-4 weeks ago. We had some test cases that were depending on this, where you have a base pointer and an offset. When you add them together, you cast the result to a bool. Right? So if it's non-zero, it's true. If it's 0, it's false. Pretty straightforward. Obviously, if it's 0 plus 0, that really can't be anything except false. That's expected. In this case, if you have an array starting at 100, you take the first element of it. The address is non-zero, so that's true, obviously. So is any other element in that array, so that's true. And then you get to this case where you're saying null plus 8. I don't know what this means, but I know that 0 plus 8 is positive. So this should be true too. Except Clang says it's not. Clang says it's false. So what happened here? So Clang realized something. It realized that the C++ standard says this is undefined behavior because the first 3 cases are fine. But the last case, you're asking for the address of some element of an array that starts at null pointer. And you can't have arrays starting at null pointers. That just doesn't make sense. So if you restrict yourself to the defined behaviors, then you realize that the offset actually never made a difference. Right? It was only false when the base was null, and if the base was not null, it was always true. So don't even bother adding offset. And in fact, if offset took some significant computation, you can just go ahead and throw that away. We don't need it. And so that's a really cool optimization, but it's also really terrifying. But fortunately, you can just run a sanitizer, and sanitizers fix everything, right? Anytime in general, if you have a strange test failure that you don't understand, run a sanitizer. So that's nice, but I actually have to come clean. I'm cheating here. So I actually have a local patch that makes this UB san check better. But in my defense, I'm actually only cheating because I want to prove another point. So what happened was, this happened during my release shift a couple weeks ago, and I had it reduced to a specific revision, and I told the compiler author with this example, like, hey, I think there's a bug in your code. Like, this should clearly be true. And I provided this repro, and they said, actually, you have undefined behavior in code. That's the real bug. And so he explained it to me, and I was like, okay, right, that makes sense, sure. But what I don't get is why no sanitizer warned me about this. And then somebody else replied in the review thread, like, oh yeah, that's true. It should be able to warn you about this. Here, try this patch. And sure enough, that worked. And it caught these failures and some other failures which we didn't notice before. And so the point I'm trying to make, and actually there's 2 points. Point number 1 is that the compiler community is really awesome. So take advantage of your community. They're great. The next point I want to make is that this was really easy to do because we are living at head, and your compiler developers live at head too. So if we had been using a toolchain from 6 months ago, it would have just been a nightmare to try to apply this patch. And so for this next slide, I kind of have to apologize. I made my slides before CppCon, and I didn't realize everybody else was going to have this slide. I'm going to talk about Hirams Law. It's probably the 10th time you've heard this week. So another category of failures that we see very frequently are brittle tests. Tests that are just testing way too much. And so basically what Hirams Law says is that people don't read the comments in your API. They just depend on what your implementation does. And C++ and Toolchains have a lot of implementations, such as ordering. So if you write your method here that computes a set and returns it as an unordered set, well, you want to be a good programmer, but you also want to be a lazy programmer. So what you're going to do is you're just going to print out the value, get the value, and then plug that into your test. Right? Very easy to do. This passes, you can check it in, go home, everything's great. This is what you should have written. So if you're not familiar with the Google testing framework, elements R is actually an ordered matcher. So what you've said is this unordered set should be in this specific order. That doesn't make sense. So if you change your standard library, either changing versions or changing implementations, this test is going to break when really it shouldn't be. So this is an example of a bad test. Another pretty fun thing is floating point arithmetic. So as you may know, A plus B plus C in math is the same as C plus B plus A, but not in floating point, right? Just precision makes things different. And so the compiler tries to respect this and not reorder things, unless you give it this flag, fast math, which basically says, go ahead and do things which would maybe change the answer a bit, because I want it to be faster. Like, go ahead, do whatever optimization you want. And I think you can see where this is going. We're going to do the exact same thing. We're just going to print out the value, get it, and plug it into our test, right? And this is obviously a bad test. Like, this is the test that you should have written. You're telling the compiler, like, only be kind of near this answer, but then you wrote a test that said be exactly this answer. You've just locked in the specific compiler optimizations at that revision. And you're not allowing the compiler to make any improvements. So what you want to do is use a more relaxed matcher, or just not use fast math. It has lots of pitfalls. So those are all the basic things the ways that things can fail. This last one, I hope you never reach this spot. This is miscompiles. This is when you've written some perfectly fine piece of code and the compiler just generated the wrong instructions. The assembly does something else. So I look like this person because it means I have to start looking at assembly. So I don't really know how to deal with this. but I can still apply just normal software engineering practices. So I already have the revision identified, so I can just talk to the patch author and say, hey, you might have a bug in your code. I don't know how to give you a repro, but there might be a bug. And sometimes that's all you need. They'll look at their code again and realize, oh, I missed a check on line 70. Try this patch, and it works. Another approach you can take is to identify the affected object file. So your test might have 1,000 object files linked in. You might build all your object files with the old and new toolchain, and then just systematically, with an efficient algorithm, try different combinations of those until you find the combination where you have one object file from the new toolchain and all others from the old toolchain, and the test fails. And when that happens, you've just identified which object file the miscompile is in. And then you can use this to compare the generated assembly, or if you're using LFVM, you can look at the IR code and compare that to the C++ code being miscompiled. And that can help you give a slightly better repro to the author.
Yep. Finally, we have another category of things that can fail, and it's performance. And here the steps to follow are quite similar to what Jordan just described for miscompiles. Usually we do a couple of reruns to make sure it reproduces, then bisect, and here there's the usual twist that because benchmarks give you a number, you have to set up a suitable threshold. And there's also the fact that sometimes you can be observing actually the cumulative effect of several different regressions during the time window in between your releases. So maybe you think you're looking for a 5% regression, and what you really have are 2% ones. And then we can either talk to the author of the patch that we got as the root cause of the problem, or sometimes, because it's not easy to hand over a reproduction, we have our own compiler performance team that looks at the code and works with the authors to try to get to a fix, or at least to explain the regression enough that we can agree on a revert. And finally, we revert it or fix it. And there are a couple of special cases here that I would like to discuss because they are quite specific to performance, and they are what we call reproducible noise. So there are things that look like regressions, and they survive increased iteration counts because they are actual performance differences in between your two binaries, but they are not necessarily caused by the change you made by upgrading the compiler. So one example of this can be when you're using PGO. So you build your benchmark first, run it to collect a profile, build it again, and use the profile to inform the compiler about how to do some of the optimizations, and then you run again and measure performance. And the problem we've seen here is that profiles are not necessarily compatible at two different revisions. So we actually have to do the same thing twice. So we build twice, collect two different profiles, build it again, and at this moment, because we have two different profiles, we can have different optimization decisions made for each binary. And the moment you get there, you will have performance differences baked in the binaries. And no increasing the number of iterations will save you here. So we have two potential solutions for this. One of them is do a longer profile collection and hope that things will get average, will converge in the end on both sides. And another thing you can do if you are not really sure about this, or you cannot, you can do everything again, and you will get all new profiles for both sides of the A/B test, and then you will get a different bias in a different direction. So this is actually an example of if you can't stabilize it, you can randomize it and average out the bias. And another, this is a really fun one, is that there's some code that is really performance alignment sensitive. So in some cases, because Intel CPUs are weird, modern CPUs are weird, you can have some piece of code that if it has the wrong mix of instructions in a 32-byte aligned boundary, you can switch from the new, quick, awesome instruction decoder to the legacy one, which is much slower. So by having things moving to a different part in the binary during linking, they will end up in different parts of memory, and you will see a performance swing, but that isn't really caused by the toolchain upgrade, because if you changed any other part of the source code, for example, things could move around and end up in a different place again. And our problem here is that the model doesn't have the compiler doesn't have a good model for this. So ideally, the compiler should be able to notice the kind of mix of instructions it's emitting in between these boundaries and move things around to get always the good alignment. But we have tried and we haven't been able to make anyone at Intel implement this in Clang. And yeah, this is kind of the same problem, because we have hermetic builds, also rebuilding doesn't help, because we get the exact same binary every time with the same alignment issues. Problem here is that we don't have a good solution for this. So in some extreme cases, we have inserted load-bearing knobs and stabilized manually some benchmark. It's not pretty, but it got the job done. But we would prefer not to do that. And sadly, we don't have a better solution right now. Yep. Oh, yeah. Sorry. So yeah, we have gone over a few performance results and test results. We have fixed all the blockers, and finally we ship it. And we are happy, everyone's happy. And by now, you might be thinking, okay, that's a whole lot of ways that things can go wrong. And we have this slide here to reassure you that it's not as hard as it seems. So when we are release scope that week, it's a full-time job, but we are not on call. We don't do special hours. We just go home at the usual time. And actually, in a normal week, we have 1-2 root causes causing all the breakage we see for testing. Also, because we have shorter release windows, that helps, because there's usually not that many patches that can cause trouble. And then you always have some UV that sanitizer improvements expose, so you go and fix that too. And mostly the fact that it can take 1 or 2 weeks is because sometimes it takes some time to go back and forth with upstream, try to come up with good reproduction cases, and this kind of involvement and debugging, it has like some days of round trip time. So it can delay your release a bit, but it's not really that hard. Not everything fails at once for every release. And now, yes, Jordan.
So as we mentioned at the beginning, this isn't just about us and how we do things. Like we want you guys to think about how can you do this at your own workplace. If we were doing this from scratch, what do we think are the most important parts? Well, obviously you need to be able to test everything. This is basically a non-starter. If you can't test your universe, whatever code your users care about, you're just throwing bits over a wall and hoping it works. So part of this might be thinking about your build system. So at Google, we do everything from source, but if you're using, say, pre-built libraries everywhere, then you might want to think about how you can update those libraries when you update your toolchain. And you also want to fix things, right? You don't want to annoy your users too much. If you just ship a toolchain that breaks people all the time, they're not going to be happy, not going to use your toolchain. So having some process by which you can fix things so that your upgrades are transparent to users would be great. In the worst case, if you actually can't fix things, at least being able to notify people that they're about to have a failure and they should fix it within some number of days, that can be useful. 80-90% of our day job is just narrowing down the culprit and producing reproduction. So this is really one of the critical things that you should figure out how to do. So reducing failures, again, just use creduce or something like that. For identifying culprits, again, we have the luxury of being a source-based, using a source-based compiler, so we can use processes to narrow it down to a specific revision. And we have tooling for this, but git bisect works just fine for that too. if you're using a binary distributed compiler from a compiler vendor, you might want to talk to them about maybe getting more frequent toolchain updates, possibly on demand, so that you can say, you can go to them and say, hey, your toolchain broke my build. It was failing at 4 p.m. and it was last passing at 1 p.m. And then they can go back and figure out which was probably the problematic revision. And speaking of which, you should have a good feedback loop with your community and with your toolchain vendor. As I mentioned, like, the community is awesome. They'll help you resolve your issues, whether it's a bug in the toolchain or a bug in your own code that you didn't realize about. So having this feedback loop is important. At the very least, you should know how to file a bug, and if they suggest trying some patch or some command line flag, you should be able to know how to try that out. And if you're a large company like Google, you should figure out some way to deal with scale, but I want to emphasize this is totally optional. Like, if you have like 10,000 files or 100 tests, just like some really small scale, when you upgrade your toolchain, you're only going to have a handful of fixes to make. You can just go ahead and make those manually. You don't need to set up any of the infrastructure that we have to do that. So I just want to close by saying that, reminding you that toolchains are just software. Like, we get scared of them sometimes. They're intimidating. They have novel problems, but they're still software. You can still just apply normal software engineering practices to fix the bugs you find. And I want to emphasize that good tests and good benchmarks are really the foundation of all of this. The better tests you have, the more confidence you can have that you're actually testing the right thing. And this frequent cadence and shorter feedback cycle actually saves you a lot of time in the long run, right? Like, not only does it spread out the work, but it also means that you only have a week's worth of commits to go through, so it's much easier to identify and fix any bugs you find. So with that, I want to open up to questions, so please ask us anything.
Hey, cool talk. So one question, do you have any measure of, when you upgrade a toolchain, like how many object files or even functions change at the IR level or change at the assembly level?
I don't think we've measured it, but probably all of them, mostly.
So I would expect, like, if you're doing it like, by week, a lot of the functions wouldn't change, like, at the IR level. Or like you're saying that they do change, like most?
They do, but not significantly. I mean, it's probably various tweaks to the way that the IR is generated in LVM. Nothing significantly.
Thanks.
Yes. So I don't have numbers from the whole code base, but we have definitely seen cases where code generation didn't change, and that's why we realized some code was alignment sensitive, because we went to the generated code, to the profile, and saw that the code was byte per byte equal, but profiles counts were different. So yeah, in some cases, for sure, the code doesn't change, but we don't have numbers for that, sorry.
Hi. When you say you switch to a tool chain, are you actually checking the compilers into source control?
Yes. So the binaries and the precompiled libraries are checked into source control. And so if you sync to that revision, you get the new toolchain. If you sync to that revision -1, you get the old toolchain.
And then how would you get to the developer toolchains, like the pre-release toolchains, whatever?
So those we store in sort of an ephemeral workspace. And so they exist for maybe a few weeks or a few months. And
so it's like a short-lived branch or something? Or?
Kind of, yeah.
Okay. All right. So, but you're using source control to basically switch between toolchains now.
Yes.
And the other question I had was, you have these weekly or biweekly releases, sometimes with patches on top of them, based on some upstream hash. Are you tagging do you share this knowledge, this work with the community in terms of tagging a release or a branch in the main LVM Git?
Yeah,
That's a really good question.
yeah, we had a slide. Actually, do we still have it? Yeah. So we do publish a tag in the upstream repository. The big problem with it is that it's manual, and it happens after the release. And so I have to remember to run the script, which I don't. Right? I have so much automation, I forget to do the manual things. So like once every 2 months, we'll publish a tag saying, we built a compiler or toolchain at this revision with these cherry picks.
Yeah, I would say, and the other thing is, I think in terms of implementing this outside of Google, I think there would, not necessarily for me, but I think there would be a lot of people that would appreciate a central build, basically a central set of release artifacts, as opposed to having to build locally. LLVM's not a huge build, but it's still a big build, and getting it all working is, maybe more than some people want to deal with, especially in CI. So if the tags were available regularly, maybe someone would step up and produce regular binary artifacts that would match those tags, and you would have a lot more people living at head, basically.
Yeah, also, we have
maybe
some...
we could use Google Compute Cloud for that. I don't know, but
we have some.
And maybe that would come at some discount cost. But I don't know. It just seems like if you're interested in having the community move this quickly, I think that kind of shared resource is something that would actually make a big difference.
Mm-hmm. Yeah, we actually have. If you look at the slide, we have some Docker images that we published with the compiled binary of that revision. I think they don't also get updated for every release. Yeah. What was the thing? It was when there was no cherry picks, maybe?
Yeah.
Yeah, so the automatic process that generates them only updates when there's a clean release with no cherry picks. So you should be able to get a fairly recent version of Clang, in a precompiled form, with not only Clang, the whole toolchain, from these Docker images.
Yeah, I'm not sure Docker image is the right distro, but okay.
Anyways, come to us later and we can discuss this and maybe make some improvements to this or make some other formats available.
Hey guys, when you're running benchmarks, are you just looking at the performance of the runtime performance of compiled code, or do you also systematically benchmark compile and link performance as well?
So usually the thing we care most is the performance of generated code. Mm-hmm. We also have some liked form of compile time regression detection, because we have a build timeout for all of our object files. So if any translation unit gets a lot longer to build, we will catch it with the timeout and we will investigate that. Mm-hmm. We have also multiple, because we compile huge protocol buffer generated files with lots of lines. We have always things that are close to the deadline, and if they get a little bit slower, we usually notice too. But we don't have explicit testing set up for compile time regressions. We rely on this kind of effect. Mm-hmm. All the benchmarking I have explained is for generated code.
Yeah, it seems like at your scale, that could be something interesting you could probably look at.
And actually, we are interested in adding that to our test suites.
Yep.
Yes.
Hi. How do you make sure that the user code, that the benchmarks that they submit are actually reproducible? Do you have tools, tips? Do you send them bug reports? How do you detect them that you need to send bug reports and that sort of thing?
So usually we have a document of best practices saying if you want us to run your benchmark, you should be able to get reproducible results. And we trust them, and then when we see some regressions and we are not able to diagnose them because they don't reproduce, at some point we tell them and stop running their benchmark until they fix it.
Oh, so you choose specifically which benchmarks you're going to run. It's not an opt-in process from the end users.
No, we have a manually curated test suite that represents mostly the huge CPU consumers, because some projects have their own micro benchmarks for things, but in the great scheme of things, they don't consume a lot of CPU at Google. So we wouldn't want to block a release based on that. If they have a small regression, in the grand scheme of things, it won't be a big regression Google-wide. So that's one factor that limits us in running all the benchmarks.
Hi, thank you for the talk. I'm Matthias. I have a question. So if we add a new warning flags upstream in Clang, is it something you look at and try to see if it finds something on your code base, or is that a different team? How does this work?
Yes, that's what we handle, and I think we compile with WAll. So
Yeah.
any new compiler warning that's a default warning is something that we'll catch.
And if it's not a default warning?
Don't we also have W everything? Or?
I don't think we have W everything, but
Yeah, anyway, we have some people working on the compiler and on compiler diagnostics, so whenever there's something interesting, it gets added.
Okay, thank you.
So you have the benefit of having the same platform for your deployment and your build. I agree with everything you say, but like some people deploy on a 10-year version of Red Hat, and they think they need to use a system compiler, and so they still use C++98 or something. Do you have advice for these people to use a compiler that is not a system compiler, and do you have like issue with the version of libc and things like that? And how can you convince people to not use a system compiler?
okay, so the question is, how can you convince people to not use a system compiler and use the one that we provide? I guess we get that for free because we could control the build system, right? We use a Bazel-based system, and so we configure a tool chain to say, this is where the compiler is. You don't get anything else.
Maybe another question, because so you live in your own bubble and you don't have to care about anything. Have you ever considered like having a ad hoc linker which might remove some of legacies that linker had for 50 years? Maybe have like a linear object file format or things like that.
I don't know of any. I don't know of any effort like that, and also we don't want to diverge much from the open source world because we want to be using mostly what everyone else uses, and even our own internal development and patches on Clang, we do it upstream.
Okay, thank you.
You're welcome.
I think we're over, so let's take your questions offline. Okay, thank you.